My name is Wes Brewer. I'm a computational scientist working as a consultant to the Department of Defense's High Performance Computing Modernization Program, working with the Productivity Enhancement and Training, or PET team. So I'd like to take a moment to acknowledge my collaborators, Chris Geyer, Dardo Kleiner, Connor Horn, and a special acknowledgement to Dr. Rich Thistle from DefTech Corporation, who provided technical oversight of this project. And so today I'm going to be talking about streaming detection and classification performance of a POWER9 edge supercomputer. And so the machine that we've deployed our AI software is a POWER9 mobile containerized supercomputer called Scout, which stands for Supercomputing Outpost. And it's a self-contained and completely transportable shipping container, meaning the entire supercomputer is installed in a shipping container, and it can be deployed anywhere in the world to provide AI support at the tactical edge. So the machine has 128 inference nodes with 4 NVIDIA T4 GPUs and 22 training nodes with 6 V100 GPUs. These training nodes are essentially the same nodes that the Summit supercomputer has, except the V100 GPUs on Scout have twice the memory as Summit's GPUs. And I should mention that the T4 GPU is essentially a half of a V100 GPU in terms of the number of CUDA cores and tensor cores, but the T4 GPU has better support for reduced precision inferencing down to N8. And it's more efficient, 3 to 4 times more power efficient than the V100 GPU. Also, each node has 2 20-core POWER9 CPUs, which are 4-way hyper-threaded, which gives a total of 160 logical CPU cores per node. So one of the primary goals of this study was to optimize the machine learning workflows of 2 production-level AI systems for Scout. The first system is the Advanced Video Activity Analytics, or AVA software. This is a scalable architecture for operational full motion video exploitation. And within AVA, we're specifically working with a component, a backend component called the Video Processing Exploitation Framework, or VPEF. And VPEF provides support for streaming detection, recognition, tracking, etc. And it's built on top of the GStreamer open source multimedia platform. And so VPEF has an SDK, and that SDK can be used to make GStreamer plugins that can be used in machine learning pipelines, such as this one. So in this case, you'll see a GStreamer component over here, and actually for the inference component, this is actually a VPEF component here. So this is a pipeline we built for actually doing the benchmarks, which I'll show later. The second system, the AI system that we benchmarked, is called the Ordnance Threat Target Automated Recognition Software, or OTTAR. And it's used for classification of ordnances. It uses either a ResNet 50 or ResNet 101 neural network architecture. And it's based on a training set of either the ORD30 data set, which contains 3 types of military ordnances, such as projectile, rocket, landmine, with 10 unique models of each type, or the ORD72 data set, which has 6 types of military ordnances. So this has the first 3 that I mentioned, the projectile, rocket, and landmine, and adds 3 more, the grenade, fuse, and scatterable. And instead of 10 unique models, this one has 12 unique models of each type. Finally, OTTAR uses the Unity physics-based VR environment to generate synthetic training images. So you could take one of these objects, physical objects, and you could scan it in using photogrammetry software to create a 3D virtual model, and then you can take that 3D virtual model and place it in virtual scenes created by Unity And by doing that, you can generate millions of images to train this neural network architecture. So as far as benchmarking methods, we looked at 4 different approaches for benchmarking Scout. The first was distributed training via Horovod. Horovod is a deep learning framework, and the way it works is by distributing the training data across multiple GPUs, and then it uses NVIDIA's collective communications library, or NCCL, to actually do a ring all reduce to average the gradients at each training iteration. The second benchmark we looked at was single stream inferencing using the video processing exploitation framework. And the way this works is by sending a video stream into the GPU and inferencing a single image at a time. The third benchmark we looked at was offline inferencing using the Inference Benchmark. And in this approach, we send a batch of images. So for example, 32 images at a time. We make a request using HTTP or gRPC protocol to an inference server. The inference server receives the request, it dispatches the batch to the GPU to be inferenced, and then responds back with a batch of results. And the fourth benchmark we investigated was reduced precision inferencing using TensorRT. So in this benchmark, we wanted to investigate how we could do inference at reduced precision, either FP16 or N8. This involves quantization, and in the case of N8, it requires both quantization and calibration. And the purpose of doing this is to be able to inference on the GPU's tensor cores rather than the CUDA cores, and be able to get significant speed ups in inferencing by doing this. So as far as results from distributed training using Horovod, we first started by training a ResNet 50 neural network architecture using synthetic data. And we did this, we scaled this up to 48 GPUs using Horovod. And as you can see here, we have the speed up on the left y-axis and efficiency on the right y-axis. So this is the blue is the speed up here up to 48, and the dashed line is ideal speed up or perfect speed up. And so the speed up is performance is quite good in terms of parallel scaling efficiency. This gives a parallel scaling efficiency of 91% at 48 GPUs. The other approach we tested was training faster RCNN object detection using wide area surveillance activity-based intelligence, or WASABI, which this is WASABI dataset that was stored as TF records. This is a dataset that's made available by the Australian government's Department of Defense. And I don't have a plot, the similar plot on this one. By going through this study, we were able to optimize, do some tunings to really get an optimal performance. And those tunings were related to making sure we were using the InfiniBand adapters correctly, and some issues related to Horovod. So one particular example I'll give is that we noticed by looking at timelines, Horovod timelines, that the negotiate all reduced times were inordinately long. And by doing some searching, I found that TensorFlow actually gives inordinately long negotiate all reduced times. And so we found a fix for this by setting a flag called Horovod _autotune. And that seemed to solve that problem. There, also, we wanted to make sure that TensorFlow XLA was being used. So this is for accelerated linear algebra and can give up to 15% performance boost. And there's some environment variables that can be used to turn this on. And also that nickel was being used and the right version of nickel was being used. There's considerable difference between in performance between different nickel versions. And so the specific tunings are all laid out in the paper. For the second benchmark, which was single stream inferencing using the video processing exploitation framework, as I mentioned before, we first created this the pipeline. So this is a GStreamer pipeline which has VPEF components, and so in order to create the benchmark, we first where we do the inference, we take a timestamp just before and just after, and then we post-process. So we send 1,024 frames through the pipeline, frames of video, and then we subtract the timings for each frame, average those to get an average benchmark value. We initially started this using synthetic video. So in this case, we had 1,024 frames of a white ball bouncing around on a black image. And then we show the performance benchmarks here. We benchmarked this at 4 different resolutions: 480p, 720p, 1080p, and 2160p. 2160p is the same as 4K resolution. And then we did this on POWER9 CPUs, T4 GPUs, and V100 GPUs. So something that we can immediately observe is that the V100 performance is about twice as fast as the CPU performance, and then the T4 GPU performance is somewhere in between. And you can see as the resolution increases, the performance starts to fall off as the resolution increases up to 4K resolution. We also did the same benchmark on real video. And so we used some sample video from NVIDIA. In this video, there were instances of cars, pedestrians, and also bicycles. And this was using the Single-Shot Detector with MobileNet V2 to do object detection and classification of these objects in the images. And so we only had video in this case at 720p and 1080p. The interesting thing about these results is that the T4, in this case, the T4 was on much similar par with the V100 GPU, and actually in this rare case, actually the T4 outperformed the V100. But actually on another system, Vulkanite x86-64 system, it got slightly better performance than the T4 on Scout. But I just show this because this is the first time I've actually observed a T4 outperform a V100 GPU at FP32. And of course, if we reduce the precision down to N8, the T4 could significantly outperform the V100. But I just mentioned this because in most cases, the V100 significantly outperforms the T4. But in these special scenarios, such as lightly loaded inferencing or lightly loaded stream inferencing, the T4 performs particularly well. And I think it was really designed for this type of inferencing in mind. Now, when we go to offline inferencing, we see a very different picture. So in this case, we use the Inference Benchmark or iBench. This is a software presented at the HPEC 2020. And I have a paper on that. The way the Inference Benchmark or iBench works is that there's a number of clients. These are HTTP clients. And each of these is sending batches of images through an HA proxy load balancer. The HA proxy load balancer is round robining these requests to inference servers, and the inference servers receive the request, make the inference, and return the batch of results. So in this case, we ran this test on a single inference node and a single training node. So the inference node has, and then we just use 4 T4s on the inference node, and we just use 4 of the 6 V100s, so we can have a 4 GPU comparison on both. And we did this at multiple concurrency levels. So for example, a concurrency of 16 represents 16 clients sending to a single server. And what is immediately noticeable here is there's almost a 4x improvement in throughput for the V100, and mainly owing to its ability to handle much higher concurrencies than the T4 GPUs. And I think across the board, this is these are the kind of the results that we typically see with the V100s, is that they're able to handle lots of data very capably, whereas the T4s tend to choke when you reach a certain point. Now, I should also mention that there's another difference between these two nodes. One is that the V100s have NVLink connecting the GPUs, which is 25 gigabytes per second, whereas the inference nodes have PCIe 3 connecting the GPUs and the GPU to CPU. So that's around 16 gigabytes per second. For the last benchmark, which was reduced precision inferencing via TensorRT, we investigated reducing the precision down to half precision, FP16, and also down to N8. But before we did that, we first did a conversion from the TensorFlow FP32 model to TensorRT FP32. And you can see that so in this conversion, a number of optimizations happen. One is that the weights get frozen, and another is that layers get fused together, and a number of other optimizations. But you can see a significant speed up, not quite 2x, but significant speed up going just from the TensorFlow format to TensorRT optimized format. Once we're in the TensorRT, we also investigate reducing that down to FP16. And so we noticed more than a 3x speed up going from FP32 to FP16. Ideally, you should only expect a 2x speed up. So what I think is happening here is that in the FP32 case, you're actually using CUDA cores. And then when you go down to FP16, you're actually using the tensor cores. Tensor cores are essentially very fast multiply and accumulate units. They're similar to Google's tensor processing units. They do one thing well, and that's multiply and accumulate matrices. So we can see like more than 3x speed up here going from FP32 to FP16. And then when we go one more down to N8, so we could only do this for the T4s because the V100s don't support anything less than, any tensor cores less than FP16. We see almost another 2x speed up going from FP16 to N8, which is what is expected. Ideal speed up is should be 2x there. And so if you look at going from FP32 in TensorFlow format all the way down to TensorRT at N8, we see a 10x speed up in performance, which is quite significant. Okay, as far as conclusions in this study, we performed a thorough performance evaluation and optimization of production level AI systems on a POWER9 edge supercomputer. In the training performance, we saw good parallel scaling efficiency, which was demonstrated up to 48 GPUs via the Horovod framework. And we found a number of tunings for optimal performance, for example, by turning on Horovod auto tune, by using the InfiniBand adapter, making sure all those settings were correct, those kind of things. In terms of inference performance, we saw that the V100 GPUs performed especially well at high concurrency loadings. From the tests we ran with iBench. We also showed that the T4 GPUs work especially well at lightly loaded streaming scenarios, especially at reduced precision. And we showed that reduced precision inferencing yielded a 10x speed up down to N8. As far as future work, we'd like to perform a similar study using NVIDIA's DeepStream at reduced precision. However, DeepStream was not supported on POWER9, so we did not include it in this study. If you do have any questions, feel free to email me at wesley.brewer@gdit.com. Thank you.